In the early weeks of 2025, the city of Albuquerque, New Mexico, was rocked by two deliberate, coordinated arson attacks. One targeted a Tesla dealership. The other, the state headquarters of the Republican Party. What investigators uncovered in the aftermath was more than a tale of criminal intent. It became a narrative decoded through chemistry. With a sticky, blue substance in a glass jar, serving as a silent, eloquent witness, in a high-stakes forensic investigation. Discovery at the scene. The improvised incendiary. At the Tesla site, amid the charred remains and acrid smoke, investigators found a small yet crucial piece of evidence. A partially intact glass jar containing a dense, bluish gel. It had a strong gasoline odor. And a glue-like consistency. Subsequent laboratory analysis swiftly confirmed suspicions. The substance was an improvised form of napalm. Gasoline thickened with dissolved polystyrene, likely sourced from household packaging foam. This gel was not accidental. It was engineered to adhere to surfaces, sustain intense heat, and resist suppression. Unlike a conventional Molotov cocktail, which burns quickly and erratically, this device was crafted for prolonged, high-temperature combustion, maximizing destructive capacity. In official forensic or legal documents, the term napalm is generally avoided, to correctly identify material classes. While maintaining chemical objectivity, the substance may be described as flammable gel, viscous incendiary mixture, or gelled fuel accelerant. Understanding napalm, from battlefield to urban arson. The term napalm itself has chemical origins. It derives from naphthenic and palmitic acids. During World War II, these acids were combined with aluminum salts to form metallic soaps, which thickened gasoline into a sticky, flame-retardant gel, revolutionizing incendiary warfare. By the Vietnam War, the formulation evolved into Napalm B. This version used polystyrene, and often benzene as additives, producing a gel capable of burning at temperatures close to 1,200 degrees Celsius. It adhered to virtually any surface, and proved notoriously difficult to extinguish. The improvised napalm in Albuquerque mirrored this evolution. Polystyrene, a common polymer, dissolves in aromatic hydrocarbons present in gasoline, such as toluene and xylene. As the polymer chains interact with these solvents, they form a gel matrix that traps the fuel, slows its combustion, and increases burn temperature and duration. The result, an incendiary mixture, with enhanced destructive potential, and extreme resistance to extinguishing efforts. Building the forensic picture. Connecting the dots. The gel was just one part of a broader forensic tapestry. Investigators recovered similar jars, at both arson sites and at the suspect's residence. These jars featured distinctive gingham-patterned lids, and, in several cases, bore handwritten labels. Forensic handwriting analysis revealed consistencies in pen pressure, ink composition, and writing style, creating a direct link. In the suspect's home, blue egg cartons, commonly made of polystyrene foam, were found. These matched the texture and color of the polystyrene-based gel, strongly suggesting source material correspondence. Spray-painted messages at both crime scenes, rendered in red and black, were also investigated. Forensic comparisons revealed matches in stencil design, paint application, and batch composition with aerosol cans and tools found in the suspect's garage. Still, physical similarities alone weren't enough. Chemistry would make the case. The analytical arsenal, chemistry in action. As an analytical chemist with experience in fire debris and trace evidence analysis, I emphasize the pivotal role chemistry played in attributing material source and constructing a reliable evidentiary chain. To turn circumstantial clues into courtroom evidence, forensic chemists employed a suite of validated analytical methods. GCMS, gas chromatography, mass spectrometry, following ASTM E1618, was definitively applied to isolate and identify volatile compounds. Passive headspace adsorption extracted ignitable liquids from the gel, revealing gasoline and degradation products like styrene monomer and toluene, clear indicators of dissolved polystyrene. Fourier transform infrared spectroscopy, in accordance with ASTM E1252, and pyrolysis GCMS, were likely applied based on standard forensic protocols. FTIR provided non-destructive identification of the polymer, through characteristic aromatic bonds consistent with polystyrene. Pyrolysis GCMS, likely performed per ASTM E1610, confirmed the polymer identity by detecting thermal degradation products such as alpha-methylstyrene and benzene. Analysts also scrutinized paint residues, dyes, and textiles. Microspectrophotometry was likely used to characterize pigment absorption spectra. X-ray fluorescence, XRF, and scanning electron microscopy with energy dispersive spectroscopy, SEMEDS, were likely employed to identify elemental signatures, including titanium dioxide, iron oxides, and copper-based dyes, that matched materials found in the suspect's home. Cloth wicks inside the jars underwent fiber analysis under ASTM E2224 protocols. This likely enabled determination of fiber type, cotton, polyester, or others, and comparison to household fabrics seized from the residence. Latent fingerprints and DNA profiles on jars and lids further reinforced the suspect's connection to the devices. This case demonstrates the essential role of forensic chemistry in interpreting material composition and degradation behavior, correlating scene residues with source materials, supporting investigative hypotheses with court-admissible data. Chemistry closes the case. Molecular proof. Every technique used added precision and weight to the narrative. GCMS confirmed gasoline and polystyrene-derived compounds. FTIR and PYGCMS likely identified polystyrene as the thickening agent. Microspectrophotometry and FTIR likely characterized dyes and paint binders, linking scene and source. SEMEDS and XRF likely pinpointed pigment elements. DNA and fingerprint evidence provided definitive individual association. This was no longer speculation. It was a scientifically supported conclusion, built on analytical results, chemical profiling, and trace evidence correlation. While official records may describe the material as a flammable gel accelerant or viscous incendiary mixture, the compositional data pointed clearly to a homemade, polystyrene-thickened fuel gel. It was deliberate. It was destructive. And, through chemistry, it was unmistakably traceable. What began as a smear of blue gel in a broken jar, became the linchpin of a complex forensic investigation. This case illustrates the power of forensic chemistry, not just to identify substances, but to reconstruct events, connect individuals to actions, and transform molecular traces into legal truth. From its wartime origins to its forensic relevance in 2025, the chemistry of napalm tells a story of destruction. But it cannot destroy the truth. Because in forensic science, it is not just about one explosive event or single clue. Like a puzzle, every compound, every residue, every trace holds a place in the bigger picture. Thank you for joining me in this case. If you found this investigation insightful, please give the video a like, share it with others who are curious about forensic science, and subscribe for more cases where chemistry meets justice. Feel free to ask questions, leave a comment, or request a topic you'd like to see covered. I'm always open to clarifying doubts and diving further into science. Stay curious and critical. Thanks for watching, and goodbye.